Okay, part one of chapter 11. So chapter 11 is all about two sample tests of hypothesis. We will have 5 different tests. In this narrated lecture, we will be only looking at 2 of the types of tests. Specifically, both will be z-tests. So two-sample hypothesis test. Two-sample test is a test performed on data of 2 random samples obtained from different populations. So example 1, exam scores of male versus female students. Example 2, exam scores of morning versus evening classes. So here we're going to try to compare to see whether there's a statistically significant difference to population. So is there statistically significant difference between the two? So for example, is there a difference in the way male students versus female students perform on a certain exam? Is there a difference between the exam scores of morning courses versus evening courses, etc.? So the 2 types of tests we're going to cover for in this lecture is the 2-sample z-test and the 2-sample z-test of proportions. So in the case of the 2-sample z-test, there's an assumption that is made, and that is that the population standard deviation is known. Okay, so it must be given to you in the problem in order for you to proceed with the 2-sample z-test. You'll be testing 2 population means, effectively comparing them to each other. So an example of a null and alternate hypothesis would be something like this, where the null would be mu1 is equal to mu2, or the population mean of sample 1 is equal to the population mean of group 2, where the alternate hypothesis would be mu1 does not equal mu2. In the case of the proportions, right, we will be looking at a sample hypothesis that says the population proportion of group 1 is equal to the population proportion of group 2, and of course the alternate would be the opposite. So let's get started by looking at just the z-test of means. So when you're comparing 2 population means, assuming equal and known population variances, we don't have to make any assumptions about the shape of the population. The samples are from independent population, that is a key. So we need to be able to make sure that the 2 samples are coming from different populations. And this will be the equation, or the new equation. So notice it's going to be very similar to the equation we've seen before, except here you're actually just comparing the difference between sample 1 and sample 2. Okay, let's just start by looking at an example. Comparing 2 population means. So let's have a look at this question here. So it says the U-Scan facility was recently installed at the Burn Road Food Town location. The store manager would like to know if the mean checkout time, so we're checking means, using the standard method is longer than using the U-Scan method, which is a method of, I guess, saying, self-checkout. She gathered the following sample information. The time is measured from when the customer enters the line until the bags are in the cart. Hence, the time includes both waiting in line and checking out. So the standard method got a mean of 5.5 minutes. The U-Scan method, 5.3. Here's the population standard deviations of each and the sample size of each. Notice that the sample size of the 2 different techniques can be different. This is not an issue since we have the population standard deviation given to us. And even if we don't have it and we're using the sample standard deviation, we could still use a variation of sizes in terms of our sample. So let's start off by setting up our hypothesis test just like we did for chapter 10. Except in this case, we are comparing 2 means, which means that our hypothesis test is going to look a little bit different in terms of just step 1, but the rest of it will be almost identical to the way we did hypothesis testing in chapter 10. All right, so let's get started with this problem. So step 1 is our hypothesis. So we have our null, and we have our alternate. So in this case, the question or the alternate hypothesis says the store manager would like to know if the mean checkout time using the standard method is longer than using the UScan method. So we have to set it up this way just to write it in language. Want to know, is the standard method, so standard, right, longer than UScan? Which means what's the null hypothesis is that the standard method is no longer than the UScan method. Okay, so let's rewrite that mathematically. Okay, so you don't have to write it this way. Let's rewrite it mathematically. So in this case, we'll say the standard method is going to be mu1, right, our first mean. So mu standard, or mu1, is greater than mu UScan, or mu2, which means the null would be mu standard method is less than or equal to the UScan method. Okay, so there's our hypothesis. The next thing we need to know, is this a one-tail or two-tail test? Clearly we can see that we have a specific direction in this question. It says longer, shorter, etc. So this is going to be a one-tail test. And then of course, just like we did in chapter 10, the side that we're testing is determined by the arrow on the alternate hypothesis. In this case, you can see that it's pointing to the right, and therefore this is going to be a right tail test. Second step is level of alpha. For this problem, let's use an alpha of 0.01. And in all problems, this will be given. And actually, it is given on the slide version of this problem. So we'll use the alpha of 0.01. Step 3. Well, what we're doing here is we have some interesting information. So we're doing a two-sample z-test. And why are we doing the two-sample z-test rather than t-test? Well, it's because if you look up here, you'll notice that the population standard deviation for both is given. So we'll say sigma 1, or let's write it in the context of the problem, sigma standard method and sigma UScan method are known. Okay, so let's go to step 4. Step 4 is our decision rule, which is effectively exactly what we've done in our previous process. So we draw our distribution. It's a right tail test. We just need our z critical value. Now remember, this is 0.01, so we need to find this area on the z table, so that would be 0.49. And when we look up 0.49 in the body of the z table, we get a z statistic, or z critical value, of 2.33. So let's set up our rejection region. So if we get a z value greater than 2.33, we reject the null and basically accept that the standard method takes longer than the UScan method. If we get a z statistic less than 2.33, we fail to reject the null. Okay, so let's go on to step 5. Step 5 is our actual test. So in this case, the z statistic equation, as we saw on that earlier slide, is that z equals x1 bar minus x2 bar divided by the square root of the variance of 1 over n1 plus the variance of 2 over n2. Okay, so let's fill in our data for this problem. So for z, we know x1 bar is given to us to be 5.5, and this is of course the mean of the standard method minus the mean of the UScan method divided by the square root. And here we're given our data in terms of standard deviations, as you can see right here, right? We have standard deviations, so we need to square those to get the variances. So we have 0.4 squared over the sample size of the standard method, which is 50, plus 0.3 squared over 100. Okay, so once we go through this process, we find that the z statistic, right, will have 2.2 over 0.064, which gives us a z statistic of 3.13. Now, a z statistic of 3.13, if we go back to our rejection region here in step 4, right, that will be somewhere out here, right? That's 3.13, and therefore it's in the rejection region. So here, what this tells us is we reject the null. And remember, when we reject the null, we're basically accepting the alternate hypothesis. So in this case, if we just go back to read our question at hand, it says, the store manager would like to know if the mean checkout time using the standard method is longer than the U-scan method. You would answer yes to that question because you are confirming this alternate hypothesis. Okay, so let's go on to the p-value, our last step, just like in the other case. So step 6 is our p-value. Okay, and remember that the p-value is the area in the distribution that is greater than our z critical value. So this is 3.13, and what you'll notice is this is effectively bigger than our entire z table. So we can just use an approximation and say p is approximately 0. Okay, so what does this tell us? It tells us that the probability that this result, where the U-scan method is faster than the standard method, is not due to chance, and it is an actually statistically significant variation of the two groups. So again, what do we conclude? Well, we again reject the null, and we conclude that the U-scan method is faster. Right, so effectively with the U-scan method, people wait less and they get through the line quickly and get out of the store quickly. Now, I want you guys to think about, as you go through this, the importance of understanding something like this, right? If you're a supermarket, would you be interested in this type of information? Well, of course they would be, right? They need to understand whether they should enact more self-checkout stands like U-scans and reduce standard methods, right? The question may be yes or no, and there's pros and cons to each of these, but this hypothesis test of checking out these two different populations basically gives us a scientific way to figure out what the supermarket should do. So remember what we call this section of our course, and that is effectively decision making using data, right? So this helps us enforce the idea of decision making using data. Okay, so what did we conclude? We concluded that the U-scan method is faster, and we rejected the null because z is greater than our critical value. All right, now for proportions. So what are some examples of when we would want to use proportions? So here's an example. The Vice President of Human Resources wishes to know whether there's a difference in the proportion of hourly workers that miss more than 5 days of work per year at the Atlanta and the Houston plants. Okay, so we're looking at a proportion. Another example. A consultant to the airline industry is investigating the fear of flying among adults. Specifically, the company wishes to know whether there is a difference in the proportion of men versus women that are afraid of flying. So let's start out by the setup. So we investigate whether two samples came from populations with an equal proportion of success. This is our key assumption. The two samples are pooled initially using our formula. This is the pooled proportion equation. You see it's called PC. And that's done by taking the number of successes in the first sample plus the successes in the second divided by the sample size of each. The z-test statistic for step 5 is calculated this way. So sample proportion 1 minus sample proportion 2 divided by the square root of the pooled proportion, etc. So this is the sample question we're going to be working with, and the next slide we'll basically go through a full solution of this problem, a worked solution. So what we're trying to figure out here is if there's a difference between the preferences of younger women versus older women in deciding to purchase a certain new perfume. Okay, so this is a test of proportion. So this is a two-sample test of proportions. Now let's read through this question and see if we can identify all the important information here. So here we go. Manelli Perfume Company recently developed a new fragrance it plans to market under the name Heavenly. A number of market studies indicate that Heavenly has good market potential. The sales department is particularly interested in whether there is a difference in the proportion of younger and older women who would purchase Heavenly if it were marketed. So there's our question. So samples are then collected from each of the independent groups. Each sampled woman was asked to smell Heavenly and indicate whether she likes the fragrance well enough to purchase the bottle. They sampled 100 younger women and found 19 would purchase the perfume, so 19 out of 100. Of the 200 older women they sampled, 62 would purchase the perfume. We're going to test the alternate hypothesis, or test a hypothesis, at the 5% level of significance. Right, so this is going to allow us to see whether or not there's a similarity or difference. Remember, why might you want to know this information if you were the store? Well, first of all, you might want to know, should you market differently? So if, for example, you found that more younger women would prefer to purchase the perfume, you may market the perfume a certain way, versus if older women were going to be purchasing the perfume because they liked it better, then you might want to market that slightly differently as well. So in this case, we just want to know if there's a statistical difference in the number of women that would purchase the perfume. This is not a perfect experiment. To make this better, you might want to know exactly what the age groups they mean by younger versus older, right? What does that mean? Is there a number? Is there a price associated with the perfume? So there's lots of different issues that we can bring up, but for us, for now, we just want to set up this hypothesis and basically test to see if there's a statistical difference between them. So once again, let's start with step 1. Now, this is a proportion. So in this case, we're going to be setting this up based on pi, right, our population proportion. So if we want to know if there's a difference, we just say pi younger does not equal pi older. There's our setup, which means the null hypothesis is pi younger is equal to pi older. So basically this says there is a difference between the two groups. So there is a difference in the purchasing patterns between the younger and older women. And the null is saying there is no difference between our two populations. Okay? So in this case, since we're just looking to see if there's a difference or not, we're basically going to be conducting a two-tailed test. Again, why? Because there's no indication of direction. We're just checking to see if there's a difference or not. Step 2, we want to set up alpha, and we find that that's 0.05 or 5%. Step 3, this is a two-sample proportion z-test. Okay. Step 4, our decision rule, done just like we did it in the previous chapter. Set up our rejection regions. Okay, so since this is two-sided, we have two critical values. So we have a negative z critical value and a positive z critical value. Okay, so alpha 0.05, what does this tell us? Well, it tells us that our z critical values are negative 1.96 and positive 1.96. Okay, so once again, our rejection regions. If we get a value less than negative 1.96 and greater than positive 1.96, we reject the null. And if we get a value between the two, we fail to reject. All right, on to step 5. So step 5 is our test. So when we're testing for the two sample proportion test, our equation is z equals proportion of sample 1 minus proportion of sample 2 divided by the square root of the pooled proportion 1 minus the pooled proportion divided by n1 plus pooled proportion 1 minus the pooled proportion divided by n2. Now, what is the pooled proportion? PC is found by taking the number of successes in group 1 plus group 2 divided by n1 plus n2. So for our example, what we have here is we found that they tested 100 younger women, so there's n1, and 19 were successes, so x1 is 19, x2 is 62, and n2 is going to be 200. Why did we label younger proportion 1 and older proportion 2? It's just the way the question was written. It doesn't effectively matter as long as you consistently follow the process. One thing just to recommend that we're all on the same page. Basically, let's stick with whatever information we're given first, like in this case, younger women is given first. Use that as sample set 1. And whatever's given second, use that as sample set 2. All right, let's find our pooled proportion for this problem. So PC is equal to 19 plus 62 divided by 100 plus 200. So our pooled proportion for this problem is 0.27. Okay, so it's like putting together the two proportions. We're saying this is like the average number of people that would like the perfume of the whole group. All right, so the proportion of younger women that would buy the perfume are going to be 19 out of 100, which is 0.19% or 0.19. And the proportion of older women that would like the perfume is 62 out of 200, which gives us 0.31 or 31% of them. So there is a proportion difference between them, but what we want to test now is to see whether this difference between the two groups is a statistically significant difference. And to do that, we must plug in those values into our equation. So z equals 0.19 minus 0.31 divided by the square root of 0.27, 1 minus 0.27 over 100 plus 0.27, 1 minus 0.27 over 200. So what is this z equal to? You have to be careful here with your parentheses and so on. This is really easy to mess up. The z is equal to negative 2.21. Okay, so let's compare that to our rejection region. So our rejection region was failed to reject region was between negative 1.96 and positive 1.96. We got 2.21, which is out here in the left tail. So there's our negative 2.21, our z-test statistic, and that's in our rejection region. So we reject the null of no difference. So what do we find? Is there a difference in the number of younger women versus older women that would purchase this perfume? And the answer is yes, there is a difference. Okay, between the two groups, between younger and older women that would purchase perfume. Okay. Now, of course, our last step, which is our p-value. So step 6, the p-value. And again, remember, this is going to be the area past our test statistic. So we had a negative 2.21. But remember, this is a 2-sample test, so we must also include the other side of the distribution, the positive 2.21, and the summation of these two will be our p-value. Okay, so now we look up our z-table, and when we look up 2.21 on our z-table, we get, let's see, 0.4864. 0.4864, so that's this area here. And so in order to get this p-value, or this region in the tail, we do 0.5 minus 0.4864, and we get 0.0136. And remember, since this is, we have to include the other side, the p-value is going to be the sum. So in this case, the p-value is 0.0272. Okay, so comparing that to our value for alpha, p and alpha, the alpha is going to be smaller since our since our alpha was 5%, and therefore this helps us further prove that we reject the null. So what does this tell us? It tells us there's a 2.72% chance that the result that we saw, or the variation we saw between the two groups, was purely due to chance. And that's a very, very low probability. Therefore, we conclude to reject the null. Okay, so we find here that the test statistic is negative 2.21, right? And that is in our rejection region. Therefore, the null hypothesis is rejected. So to put it another way, we reject the null that the proportion of young women who would purchase Heavenly is equal to the proportion of older women who would purchase Heavenly. Now, if we wanted to know whether or not older women preferred Heavenly over younger women, we would need to then conduct a one-sided test. Because remember, the one-sided test would kind of readjust this critical value, and therefore the test would need to be redone before we can move to that point and conclude older women prefer the perfume. Think about different ways you can use this, particularly if you are majoring in marketing and anything in that type of work, because this will allow you to basically make decisions about whether or not you market a product, who you market it to, etc. All right, that's the end of the part 1 of chapter 11. Part 2 will contain tests for 3 different types of t-tests, and that will be up shortly.